All right, welcome to The Explainer. Today we are all about finding the absolute peak. I'm talking about the highest highs and the lowest lows. You know, stuff like nailing peak profit for a business or finding the rock bottom point of a cost curve. Calculus gives us the keys to the kingdom here. So let's jump right in. So, think about it. You might be trying to maximize profit, right? Or maybe minimize your costs for a project. Or hey, maybe you're just trying to figure out the highest point a ball will reach when you throw it. The goal is always the same. Find that absolute best value. The real question is, how does math give us the map to actually find it? Okay, so here's the best way to picture this. Imagine any function is like a giant, sprawling landscape full of hills and valleys. Our mission, should we choose to accept it, is to become expert explorers. We're going to gear up with some serious calculus tools to find every single peak and every single valley on that map. All right, first things first, we need to define our landmarks. You know, just like on any map, you've got your smaller hills, and then you've got the one true highest mountain in the whole range. Well, in math, we have a name for these, extreme values. And this difference between local and global, it's super important. A function can have a whole bunch of local peaks. Just think of them as little foothills. But there can only be one absolute highest point across the entire map. That's our Mount Everest, the global maximum. Okay, so how in the world do we actually find these special points? Well, our very first clue as explorers is to look for spots where the ground is totally, completely flat. And this is our main target. Remember, the derivative, that's f prime of x, is just the slope of our landscape at any given point. And what happens right at the tippy top of a peak or at the very bottom of a valley? For just a split second, the slope is 0. The ground is perfectly level. Now, this leads us to a really important distinction. We've got stationary points and critical points. So here's the deal. All stationary points are critical points, but it doesn't work the other way around. To find every possible peak and valley, we can't just look for the flat spots. We also have to scout out any sharp, pointy corners, places where the derivative might not even be defined. And hey, here's a crucial heads up for our little expedition. Just because you find a flat spot doesn't mean you found gold. Take a look at the function f of x equals x cubed. Right at x equals 0, the slope is 0, so yeah, it's a critical point. But if you look at the graph, it's not a peak and it's not a valley. It's just a flat spot where the curve takes a quick breather before heading up again. So not every critical point is an extremum. Gotta remember that. Okay, so we found our potential landmarks, right? Our critical points. But now what? How do we tell if we're standing on a glorious summit or stuck at the bottom of a dreary valley? Well, for that, we need to break out our first major tool, the first derivative test. And this is just beautiful in its simplicity. The sign of the derivative tells you which way you're headed. Positive, you're going uphill. Negative, you're going downhill. So just picture it. You're climbing up, 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 and then you start going down. What just happened? You must have gone over a peak. That's a local maximum. It's as simple as that. Now, the first derivative test is totally reliable. It always works. But, sometimes it's a bit of a slog. Luckily, we've often got a shortcut. That's where the second derivative comes in, f double prime of x. This tells us about the curvature of our landscape. Is it shaped like a cup or is it shaped like a cap? And here's why this is so great. It's all about efficiency. Think of it this way. If the second derivative is negative, the curve is concave down, kind of like a frown. Well, where's the highest point on a frown? Right at the top. So you found a local maximum. If it's positive, the curve is concave up, like a smile. And the lowest point is right at the bottom. Boom, local minimum. On a time test, this can be an absolute lifesaver, way faster than checking a bunch of intervals. All right, so we've gotten really good at finding all the local hills. But what about Mount Everest, the one true highest point of our entire function? To find that absolute global maximum, we've got to expand our search. It's not just about the flat spots anymore. Okay, listen up, because this is the part almost everyone forgets. The highest point in the entire landscape might not be a nice, smooth peak. Nope, it could be hiding in plain sight, right at the very edge of the map. You have to check the endpoints of your interval. I'm not kidding. This is probably the #1 mistake people make on exams. They do all this brilliant calculus, they find all the local peaks, and they totally forget that the highest point might just be a cliff at the very edge of the park boundary. So let me say it again. Always check the endpoints. Don't let that be you. Okay, now for the really cool part, the payoff. Let's add some seriously powerful shortcuts to our toolkit. We're talking about methods that can solve some of these problems with zero calculus. For anyone taking a competitive exam, this is an absolute game changer. Seriously, just memorizing a few of these standard results for trig functions can turn what looks like a scary 5-minute calculus problem into a 30-second cakewalk. It's the perfect example of how spotting patterns in math is basically a superpower. It'll save you a ton of time and headache. All right, this next tip is pure gold, especially if you're prepping for an exam like the NDA. It's called the AM-GM inequality. That stands for arithmetic mean, geometric mean. And trust me, it is an incredibly powerful tool for finding max and min values without touching a single derivative. This little inequality is the secret sauce behind so many classic optimization problems. Here's a classic. You've got a fixed amount of fence, and you want to make the biggest possible rectangular yard. What shape do you make? A square. Why? Because the AM-GM inequality basically proves that for a fixed sum, your perimeter, the product, or area, is biggest when the sides are equal. No calculus required. It's just elegant. So, there you have it. You've got the map, you've got the tools. From the tried and true derivative tests to some seriously clever shortcuts, you are now officially equipped to find the highest and lowest points on pretty much any curve you can imagine. The only question left is, what are you going to optimize first? Thanks for tuning in.